Okay, alrighty guys. The Day Daddy here again, and just want to start as always by saying thank you for taking interest in my channel, and I really hope that the content I provide is useful for you guys. If you do appreciate it, I really love you hit that like or subscribe button so I can continue to grow and continue to provide you guys more quality content. Okay, so now we got that out of the way, let's get down to our topic for today. And today we will be discussing, optimization in data science. Um, and this is kind of a parallel to the other, series that I'm doing on neural nets from scratch, because neural nets, obviously need some sort of optimization. And so I figured that since optimization is kind of a topic in its own right, I would cover that in another series. So this is kind of the start of another series that goes along with neural nets from scratch. That is, just basically an overview of what optimization means in data science, how it's normally used, how it's implemented, some of the common algorithms, all of those things we'll cover here. And I just want to do a short video, just as an intro to kind of familiarize us with the different flavors, so to speak. So really there's the main algorithm that everything else is kind of built off of, and that is, gradient descent. That is at the core, the crux of optimization data science. And to really understand everything else that we do, we need to understand gradient descent. And I just want to say that all of these iterative optimization algorithms, these are not the only ones, and also gradient descent doesn't have to be applied to data science problems. Gradient descent can be applied to many different areas for optimization. It's not just uniquely for data science problems or machine learning problems. It just happens that this works very well for the types of problems that we are trying to solve, and the computational intensity that typically goes along with those. So anyway, let's start at the beginning. So gradient descent. What is gradient descent? Well, gradient descent is an iterative optimization algorithm that looks to, well, that's actually, there's back up for a second. There's two kinds. There's two different flavors within gradient descent even. So there's just pure basic gradient descent where we take the full training set, and we want to update our parameters for every single data instance. So, and it's kind of denoted here, this formula, this equation. So we have a set of parameters or a set of weights or however you want to think about it, and every single time, we pass a set of x's or an x value, or however this is defined, we pass something in, we activate that function, and we get our gradients. Every time we do that, we're going to subtract, well, that's our learning rate, so we multiply by our learning rate, but we take this total term here, and we're going to subtract this from our weights, and we're going to update that every time. So that's kind of the big deal here, is that for pure gradient descent, we're doing the full training set for every data instance. And as you can kind of guess, this is pretty computationally intensive, because we're doing it for the full training set and we're doing it for every data instance. So, do we really need that? Do we need to do that? And that's kind of what we'll explore as we go down and we talk about the other algorithms. But it's the simplest optimization algorithm. Its primary function is to iteratively move in the opposite direction of the gradient. We kind of already talked about that. Until the max number of iterations is reached or a stopping rule is applied, and we'll talk about those a little bit later on in the series. And then there are these following basic steps, and these are true for all of the algorithms, whether it's gradient descent, stochastic gradient descent, stochastic gradient descent with momentum, atom, all of those. They follow all of the same kind of basic steps, just with more complexity. But we want to initialize our inputs, so we want to initialize our weights in the beginning to some value. Could be random, could be something that you set just to make it converge faster, but just initialize them in some way. Okay, and then we select the learning rate. So that's that eta value, or this weird looking n thing here. And then we need to calculate the gradient, and which we talk a lot about that in the other series about neural nets from scratch, is how we actually, the nuts and bolts of how we calculate this gradient. Then we need to adjust the inputs, the weights, with the gradient. So we're doing that here. And then we need to iteratively do this. So just complete or repeat this process 2 and 3 until some condition. Like we said, until we reach a maximum number of iterations, or we have significantly reduced the error to some satisfactory level, or there's a litany of things it could be, but those are two common ones. But basically, we're just going to keep doing this until we're satisfied in some way. Okay, so that's kind of the basics here. So now, how is batch gradient descent different? With batch gradient descent, now we're still focusing on the full training set, but now we want to update once per batch. And in this case, the batch is going to be the full training set. So basically, you're equating the batch size to the full training set, and then rather than updating for every data instance, we're just going to update once for the full training set. So it cuts out a whole lot of updates and a whole lot of computations. Now, you may have to run longer to optimize in this case, but it cuts out a lot of computational intensity, even just moving or equating the batch size to the full training set and only updating once. So that's the major difference here. There's not really a whole lot of difference between these two different flavors, just a slight tweak here. Okay, so now let's hop down and let's talk about stochastic gradient descent. And this is kind of the workhorse that everything else builds off of, because we encountered a problem here. The problem with pure gradient descent is that it's computationally intensive, or too computationally intensive for our liking. So the question is, how can we reduce that level of complexity? Well, do we really need the full training set every time, or can we just take some subset of that? And that's kind of the whole idea. Is stochastic, meaning that we're just going to take a statistically random or a randomly sampled part of the full training set, and we're going to make that into what's called a batch, or a mini batch. And I'll draw it out in a diagram here in a second, but basically we're just going to randomly sample a collection of data points from our original full training set, and we're going to make that into a batch. And then we're going to update, at least in just pure stochastic gradient descent, we're going to update for every data instance. One thing to note here is that all the data in the training set must be included in our mini batch. So it'll make more sense in the diagram when I show it in a sec, but basically, just because we're randomly sampling doesn't mean that we can just take random samples and just leave some of the data unused. We need to randomly sample in a way such that every time we don't replace the sample, and that we continue to pick different instances that we didn't pick before. And hopefully that'll make more sense when I show or I draw the image here in a sec. But then we look at our equation here, and this equation, for all intents and purposes, is the same as it is here. It's just broken up into two pieces. You notice that there's this g, which is the gradient of the activation function of x, or our inputs. And really all it is if we sub this in here, we're going to arrive at the same, what am I trying to say here? The same group of parameters. And it's just this shorthand notation for x equals x minus from programming. So not really much difference here in the actual the formula itself. So we're still doing the same thing. We're still following these four rules. And just to note here is, to improve the computational power and storage requirements, we can add the idea of mini batches. We've already talked about that. Randomly choosing the subsets. And one thing to note here too is, since we're not looking at the full data set, in this case we're just taking a random sample of it, we're introducing quite a bit of noise. And that's could be a problem, because And I'll show that too in a second, just so we're very clear. But that could also be a problem, because now it's going to be harder for us to find the optimal solution because we have less data points to use. So it's going to look a lot more jerky, or the curve is going to look a lot jerkier as we are moving towards the optimal minimization of the error. And again, we'll see this going forward in a lot more detail, and I'll try to draw it here as well, so it makes more sense. Okay, and now we move to Stochastic Gradient Descent, which is really the crux here. This is the workhorse, and it's the same thing as pure Stochastic Gradient Descent. The only difference now is that instead of for every data instance we update once per batch. So we're taking different batches of our training set, and then we're only updating once per the batch. So okay, while we're thinking about that, let's draw a couple things. Okay, so the first thing I want to show is what a mini batch is. So okay, so hopefully I can draw here where everybody can see. But all right, so this is going to be MB for a mini batch. Okay, and let's think about this as our training data. So let's call it TD. Okay, so and for our training data, we have all of these instances. We'll think about these as rows and maybe like an SQL table, or even like a Excel workbook, or whatever you want to think about this as. But these are all, each row is an instance of data, and that data can be further divided into columns where we have different values. Let's say this is some X input 1, and this is X input 2, and this is 3, and so on and so on and so on. And then we have some target value, so we'll call this Y. Okay, and so we have all these instances and all this different data, but really we want a smaller. Wow, man, I can't draw today. Not that I ever really can, but and we want a smaller mini batch. Mini batch. All right, so how do we go from this training data to our mini batch? Well, we're going to randomly take different instances. Let's say, for example, we take 3. So we're going to take this instance, we're going to take this instance, and we're going to take this instance. I just randomly sampled those. So this is going to go here, this is going to go here, and this is going to go here. Okay, so that's one mini batch. We'll call this mini batch 1. But now we need another mini batch. So now we can't use these instances we've already put in this mini batch. We need new instances. So now let's say, all right, we're going to get these. We'll do this a circle. And we're going to get 3 more. All right. And now these are going to go down here. And this one's going to go down here. And these are going to go down here. But anyway, you get, and this is mini batch. Mini batch 2. All right, but you get the idea. So we're just taking these and we're putting them in these mini batches, and we're going to do this iteratively until we go all the way through the training set and we get different mini batches. You may be asking, well, what if the number of instances isn't evenly divisible into the mini batch? Well, we'll have a mini batch that is smaller than the others that just contains whatever the remainder is. So that's kind of how we take care of that, and that's what a mini batch is. I know the drawing was bad, but I mean, hopefully this kind of gives you guys an idea of what that is. So, all right, now on to the next point that we wanted to talk about, or I wanted to talk about. Yeah, we can go ahead and clear it. All right, so the second thing is over here we said this could introduce, or possibly might introduce, a significant amount of noise in our data. Okay. So let's say, for example, that we had a graph, okay, and we had some points, Ooh, man, it's a bad one. Yeah, so we have some points and some points. Sorry, bear with me. It's hard to draw with a mouse. Okay, and there we go. So we have some points. So this would be pretty easy to understand with gradient descent if we were kind of, and the idea of gradient descent is we're hopping, we're trying to hop down and we're trying to find, where the function is minimal. Okay, so the more points we have, the easier it kind of is to see what this curve is and to follow it down. But if we only sample, like we said earlier, this is a kind of an extreme example, but say we only sample 3 points. We say we get this one, and this one. Okay? And we redraw that over here. So we're going to redraw. And I'll just use red again. But we have a point approximately here, and approximately here. So now we can see, if we only have 3 points, it's much harder to see the shape of this line, and it would even be much harder for the computer to figure out, okay, where do we go? What path are we trying to follow? So with less data, especially randomly sampled data, we could have, these, it could be, maybe we have, no, sorry, go back. Maybe we have this one, and this one, and this one. I mean, that doesn't look like the shape at all. So, point being is that, this is an extreme case, but when we take those small mini batches, we kind of lose the original shape, and it makes it hard, or introduce a lot of noise, because it's hard to pick the optimal gradient solutions that pull us closer to that global optimum solution, or that global minimum, shall we say. So, and this will become clear as we go through these videos. This is kind of a really high level example of why that is. So, okay. So, already running kind of long here, so I'll try to move quickly through these next ones. But okay, so that's the idea behind stochastic gradient descent. And then we have another problem. Okay, so we introduce this noise into our data. So how do we deal with that? And then that's what these two algorithms kind of try to do, is they try to address this problem with noise. So and everything's the same here. So beyond this point, we're always going to be using a mini batch, and we're going to be updating once per batch. So for SDGM, Atom, basically everything more complex than this, we're going to be using the same kind of idea. And you'll notice we've introduced a new piece here, this momentum parameter, and we've also added it to our parameter update. So, and we'll get into that in more specifics later, but basically all we need to know for now is that we're trying to use momentum, or the current gradient, and a moving average with respect to the previous gradients, or the momentum is what we're calling this, to actually help us converge faster, to help us avoid, or help us cut through this noise that we just created, and actually find the optimal solution more quickly. And that's what we're trying to do here. And that's what this little note says. And in Atom, we take it even a step further. We're like, all right, well, this isn't good enough. We're not doing a good enough job here. So what else can we do? Again, we're randomly choosing our mini batches, and we're updating once per batch. And actually, just want to say this really quick because I almost forgot. But Atom stands for Adaptive Moment Estimation. So, you'll hear a lot of people refer to Atom, and it's a default optimizer for pretty much every Python package and a lot of other packages like in R and everything else, and you'll hear Atom. But really, it's stochastic gradient descent with adaptive moment estimation, excuse me. And so you get this Atom, A-D-A-M. That's where that comes from. Okay, So now you see we've introduced a lot of things here. We still have the momentum, and now we have what's called a momentum uncentered variance. And really all we're doing here is now we're taking the moving average of the exponential weight of the gradient. So we've added basically a new way to help us converge faster. And what this does really, for all intents and purposes, is this just really it heavily weights the momentum factor in the early stages of our algorithm, or the early iterations, so that we can really drive down quickly to get close to the gradient, and then it relaxes as, this t is for time step, and it relaxes as these time steps go on. So we're just trying to really drive down as quickly as possible to get close to the optimum, and then we can relax the momentum off, and let the algorithm finish out more naturally. So, okay, that's a pretty good overview, and we'll get into each of these in more detail with notebooks and code, going forward from here. But I think this gives a really good summary of a lot of the optimization algorithms that you will see in data science. Specifically Atom, it's the default, and you'll probably also see SGD. So those are two that you definitely should know, going forward, just for your own sake. So, all right, guys, that's it for today. Again, if you found this helpful, I would really appreciate a like and a subscribe, so I can it helps me produce more content, and also leave some comments if there's things you didn't like or I can do better, or things that weren't explained well, and just give me some feedback. So anyway, guys, thanks, and I'll see you in the next video.